In this video, we're talking about similar polygons, and we will eventually get to more specifically similar triangles, but we're going to talk about any polygon. Remember, that is just three or more sided figure. So for example, we have these quadrilaterals, and these would be similar as long as these two polygons have corresponding angles that are congruent and the corresponding sides are proportional. Remember, we talked about ratios and proportions in the last video. So that just means that they would all the ratios are reduced to be the same thing. All right, so for example, if I said let me see what I said. A, B, C, D, H, I, J, K. So if this was congruent to that, B was congruent to I, C was congruent to J, and D was congruent to K. And then let's say that this was 1, 2, 3, 4, and this side was 2, 4, 6, 8. Then notice that all of the angles are congruent, and then the sides are proportional. Notice that all of these sides are twice as big as those sides on the left. So I can say those two polygons are similar, and here's our similarity statement. Remember how we would write a congruent statement between triangles? Well, a similarity statement is going to match up those letters that go together. All right, so you have to pay attention to order still. But notice that when I write similarity, I don't have that equal sign like I do in the congruent part. All right, it's just the top squiggle. That means similar. And when we write a similarity statement, that is different than writing a statement of proportionality. Proportionality means I have to write a bunch of proportions, which means I'm setting ratios equal to one another. So for example, if I wanted to say AB and HI, those are proportional sides. So I would say AB over HI would reduce to be the same thing as BC over IJ. And then we can write a whole bunch of them. So we could also say that would be the same as this side over this side. So DC over KJ. And then we can also have AD over HK. So this is what we call a statement of proportionality. We're writing out all the proportions that are equal to one another. So in the diagram, we're going to complete our statement of proportionality and our similarity statement. So triangle MON is going to be similar to triangle GHI. So I would say triangle GHI. Notice that I went single arc, double arc, no arc, single arc, double arc, no arc. And then for our statement of proportionality, MN would be similar to, or be over GI, and that would be equal to ON over HI, and then MO over GH. Now, how do we use that? Well, we can find missing sides now when I have a proportion. So if I have I have 16 here. 16 is ON, and we said that would go over HI. So I would put 12 right here. And then 10, that's the GI label. So now we're using this one. So we use this too. So this one was here. This one was here. Remember, we can switch sides in a proportion. And so MN would go on top of the 10. So that would be X. So I could solve that for X. So I would cross multiply. 12X equals 160. And then divide by the 12. And that would give me X is, well, it's going to be 13.3 repeating. So let's do a fraction there. So X is going to be 40/3. All right, so let's do the other one. So here I have 16 in the denominator, that's ON. Okay, so then HI would have to be in the numerator. Okay, remember we're allowed to do the reciprocal. So then 8, that's the GH, so that would be over our MO, which would be Y. So now if we cross multiply again, we get 12Y equals 128, and then divide by the 12. Again, I'm getting a repeating decimal, so I'm going to leave it as 32 thirds, and that would be my Y. Keep in mind that with proportions, they typically actually won't be exactly whole numbers. Very rarely do we get whole numbers, so if you get a fraction or a decimal, that doesn't mean you are doing it incorrectly. All right, so scale factor. We've talked about scale factor when we were doing dilations, and remember that's just the ratio of your corresponding sides. And I will add in here, it's the reduced ratio of the corresponding sides, so make sure you reduce your fraction. All right, so you are constructing a rectangular play area. Right away when I see that, I'm going to draw a rectangular playing area. All right. A playground is rectangular with 25 meters long and a width of 15 meters. Okay, so 25 and then 15. The new play area will be similar in shape, but only 10 meters in length. So it's like I'm taking up part of this playground to create a new play area. So that will only be 10 meters in length. All right, so it says find the scale factor of the new play area to the playground. So which sides will be corresponding? So it's going to be the lengths will be corresponding. So I would say the 10 and the 25 match up. Now, I want to see how it's worded. The scale factor of the new play area to the playground. So I want to do the new play area one first. So that would be 10 meters over 25 meters. And then if I reduce that, then I can get 2/5. Notice that when I write my ratio, I'm not writing my meters anymore. So if I start with meters, remember those are the same units, they cancel out. And this is my ratio. So my new play area is 2/5 of the whole playground. So then it says find the perimeter of the playground and of the play area. All right, so keep in mind that if 10 is 2/5 of the 25, then this width right here has to be 2/5 of 15. So if I do 2/5 of 15, and that's going to give me a width of 6. So the width of this playground is 6. So I need that in order to find my perimeter. So my perimeter of my playground is simply 25 plus 15 plus 25 plus 15. So that's 50 plus 30, which equals 80 meters. And then my play area is 10 plus 6 plus 10 plus 6. So that's 20 plus 12, that'll be 32 meters. Notice that if I were to do the perimeter, 32 meters, and divide the 80 meters, go ahead and do that, see how that reduces. You should get the same ratio. Okay, notice I can divide them both by 16. And I would get 2/5 again. So that those perimeters, that linear distance, should be in the same ratio. Now a scale drawing, so if I have a drawing that is the same shape as the object it represents, this happens a lot in like architecture, engineering, things like that. So a scale is the ratio of how it describes the dimensions of the drawing as related to the actual dimensions. So here we're talking about not just two random shapes, but now we're doing the miniature version compared to the actual one that it's representing. All right, so we buy a 3D model of the Willis Tower. in Chicago. The actual height of the building, including the television antenna on top, is 1703 feet. So I'm going to draw the Willis building, and it has like a TV antenna on top. So it's saying all of that we know is 1703 feet. All right, but we're going to make a model, and our model, the green is the model, is 29.4 inches tall, including the antenna. So this is 29.4 inches tall. And then this part right here is 4.4 inches. Okay. So keep in mind too, I'm doing different units, aren't I? So remember what we talked about in ratios and proportions. If we are going to be doing any kind of ratio, we need to have the same units. So let's go ahead and convert 1703 feet into inches, which means all I'm doing is multiplying by 12. So I'm going to have 20,436 inches for my height of the building. So now it's asking, what is the height of the actual antenna? Well, the antenna in our model is 4.4 inches compared to the whole height of the building, which was 29.4 inches. So we're going to set that equal to, now we know the actual height of the building is, we just said it was 20,436 inches. So we should be able to figure out then what is the actual height of the antenna in inches, and then we can convert that to feet if we want to. So cross multiply, so you might want to get out your calculator for this. So 20,436 times 4.4 is equal to 89,918.4. That's going to be equal to our 29.4x. And now we can divide by the 29.4. And that gave me 3,058.45 if I round that. So it's roughly that. So that's in inches. 3,000 inches is kind of hard to wrap our brains around. So let's go ahead and convert that back into feet. So if I'm going to convert inches to feet, I'm going to divide by 12 this time. I know I'm going to have a less amount of feet. So this is equivalent to 254.9 feet. So that's how tall the antenna is. It's a very big antenna. It's not like your TV antenna that's on your house. Okay, and then it says about how many times as tall as your model is the actual building, including the antenna. So they're really asking us for the scale of our building to model. So notice that it says how many times as tall as your model is the actual building. So we're going to be doing building first over our model, because it's saying how many times as tall. So big versus small. So we're going to take our 20,436 inches and divide it by the 29.4 inches of our model. So if I do that on my calculator, that gives me 695.1. And remember, this does not have units. This is a ratio. If I did a actual fraction, it would be this fraction, which that's not really what we mean when we ask how many times as tall. So this is actually a little bit better answer for this situation, because it's 695 times as tall as our model. All right, so it's a lot bigger than our model, right? It's not actual size. Okay, so in our class, we'll do some more practice with our similar polygons.